So we continue in this travel to navigate these other dimensions that are in the universe and within ourselves with Ida Momennejad. Ida Momennejad is someone that we know since long because she has been collaborating and working with Ivana and also with me since 2010 on different occasions. And she is one of those who's really cherishing the luminosity, as Monica was saying, of their friendship, intellectual and emotional exchange, and of conversations as one of the highest achievements. Ida is a neuroscientist, a computational neuroscientist at Columbia University. She did her postdoc in Princeton, PhD in Berlin, BSc in software engineering in Tehran, Iran, where she comes from, and MSc in philosophy of science in Utrecht. She uses artificial intelligence to study how brains build models of the world and how communication networks of multiple people shape collective memories and collective behavior. Her work uncovers the brain's algorithms for building cognitive maps and replaying the past to learn and update relational structures of or models of the world. Maybe I shouldn't explain exactly scientifically how this is happening because she will do that. But what is interesting is that in the collective memory line of research, Ida is using graph theory and experiments to study how conversational networks shape collective memory. And she uses multi-agent simulations to quantify systemic injustice. And that's something that we also want to talk about. Systemic injustice in institutions, comparing simulated policy that can change collective behavior in the long run. So her work is very important for us on a personal level because of our friendship and this luminosity of this friendship, but also because of her scientific unfolding. Thank you, Ida, for being with us.
Thank you so much, Elena. I am going to...
Mic is not on.
Oh.
I'm unmuted.
Maybe.
Can you hear me?
Oh, there we go.
Yes.
Okay, perfect. So thank you so much for that introduction. It's a pleasure to be back with you guys. And I'm going to share my screen and let me know if you see the presentation loading. Okay, perfect. All right, so thank you so much for this invitation. Before starting to talk about what I do, I've been enjoying the talks that have been going on, and I've always enjoyed conversations with Ivana and Elena and everybody else there. I just wanted to say, I hope that I can share a little bit of my practice, not just content. I would be sharing a little bit of screenshots of what my environments where I work in terms of coding looks like. And I'll say a little bit about the embodied experience of the quarantine on how I feel about sort of science as practiced in predominantly Western institutions. So the kind of work that I do evolves around trying to understand how we as humans learn and build models of the world that guides our behavior. Importantly, there are two different parts to my research on this. One is using fMRI, electrophysiology, epilepsy patients, artificial intelligence, computational models, machine learning, that is in the individual brain level. So there, I study how a given individual, a given agent, a given brain learns models of the world that we call predictive cognitive maps. And I'll tell you a little bit why we call it that. But another part of my work focuses on using graph theory and network science and then experiments with multiple people who study the same material and then talk to each other and then take a test on the material before and after conversations, because we wanted to study how the shape or the structure of the network of communications would sculpt their memory and behavior. For instance, right now, a lot of us from many different disciplines, as is common of Elena's sort of curation, a lot of us from many different disciplines are communicating, and there is a particular structure to the interactions that we are having, the network of interactions, and it's changing all of our memories, sort of synchronizing our models of the world or highlighting where our models of the world differ or can learn from one another. One thing I want to say is that although I'm a computational neuroscientist, I don't see myself necessarily as just operating within a Western tradition of knowledge, and I'm not talking about necessarily spiritual traditions per se. Omar Khayyam, who lived 1,000 years ago in Iran, who in fact designed a very precise calendar, and the summer solstice, it's called Tirgan, it's a celebration in the ancient Iranian culture, in fact, in order to figure out the solstices, spring solstice being the beginning of our new year. This calendar has been used for 1,000 years. Used a lot of mathematics, a lot of geometrical shapes, and also poetry in order to express his ideas. And so I find myself constantly going back to that, and I'm being a little self-indulgent by putting figures from some of my papers around, populating this slide around Khayyam's scripture, and putting around the kinds of figures that I produce in my research, which again has to do with making graphs or drawings or matrices or equations or connecting the dots. And I feel like it's important to recognize the profoundly Middle Eastern background to a lot of mathematical work in science. Working with Ivana, it really changed, I think, my way of understanding not just what I was doing and not just reflecting on what I was doing, which was during my PhD in Berlin, but also reflecting on my own science, reflecting on what it meant to acquire a certain kind of knowledge, what it meant to practice a certain kind of knowledge. Francisco Varela had this quote where he said, knowing something is not really distinguishable from how we know it, how we come to know it. And the practice of science, the way that we do it, and the way that we did it when I was doing my PhD in Berlin was very white male, hierarchical, not many immigrants. There was a very strict hierarchy. And talking to Ivana and talking to just entering the space of her artwork, for me, was a kind of almost, I would say, a healing process. In fact, I would say that it was an antidote to the amount of European white male sort of pedigree that was sort of reaching me, and I was embedded within it. And I think kind of shielded me like an immunity bubble against being so involved in that I would forget that there is some systemic issues going on. And I hope that you can see in the years that followed, this experience, this lived experience, showed also in my research, in my academic research. It relates to this idea that I wrote in a manifesto and presented at Guggenheim together with Elena and Ivana in 2012, this idea of knowledge activism, where art and science are different modes of knowing, one through felt embodied experience and one through looking at it from a third person perspective. And I think that they need to go hand in hand. In order to understand systemic oppression, for instance, you might have experienced it, but if you're European white male, you might not know what it feels like, but then we can build a model so that others can see. So hopefully we'll get to that. I'm just showing you this because I want you to see what my daily sort of life, also what my instrument really looks like. Yes, I go in the scan, sometimes I collect data from scanners, sometimes I have human experiments on subjects, but really most of the day I am speaking to a laptop alone in a room with this language that you can see. In this case, this is Python. Writing colorful code on a dark background for hours and hours and hours and creating figures like the ones that you saw. And so for those of you, this is mostly what the practice of a scientist looks like these days, because the majority of your time is spent writing, talking to others, and also coding. Another thing that the practice of scientists right now in New York City, where I live in Brooklyn, is going to protests every week, sometimes every day, depending on how sort of busy that week is. On Twitter, there is an entire the Black in STEM and a lot of different hashtags where look at the experience of people of color and women of color in academia. There is another one where it discusses that white women in the United States are not really underrepresented minorities. I think in Europe, it might be a little different because the statistics of Europe is way worse than the United States in terms of women in science. But we try to talk about being queer, being people of color, being immigrants in science, and our experiences of systemic racism and our experiences of both interpersonal and systemic racism there. And for those who can't feel it, this is the sort of way where I have this paper. You can take a look at it if you don't get the chance to sort of ask a lot of questions during the talk. How to use models, computational models, and multi-agent simulations to simulate and show to someone, hey, here's a virtual world that I created. Look at this world. Look at 1,000 conversations that happens here. Now look at this policy you're talking about that's supposedly going to correct the injustices. Let's simulate computationally different policies that you want to try in this world to reach justice, and let's see which one is better. So that's the direction that I was mentioning, that both in terms of activism on the streets and activism with science and engagement with art as a way of uncovering, sort of giving words or giving a feeling to the experience that is latent within us of oppression in academia. With that introduction, I just want to say a little bit in the remainder of the time that we have about the kind of science, the content of the science that I practice. What do I do? I'm very interested in the algorithm, finding out what are the algorithms that our brains use for learning, memory, and planning. Another sort of cultural note, the term algorithm comes from Al-Khwarizmi, another former Iranian mathematician who created the earlier notion of this. Again, I don't consider this a predominantly Western science sort of approach. Whether you're traveling on the subway from one location to another, if you're playing chess, your brain is using multi-scale representations of the world that are useful for its purpose at that moment. And depending on the goals that you define for yourself or the world defines for you, that changes the kinds of representations that your brain uses, because then it becomes more efficient at engaging with those goals and achieving those goals, whether set by society or by yourself. And this is one of the important aspects of my research involves how the goals that we have shape our models of the world and vice versa. For instance, Tolman, who was a very politically active scientist in the early 20th century, so active that he was fired from Berkeley, I think. He was in Berkeley. I don't know if he was fired from somewhere else and then Berkeley or also from Berkeley. He was extremely politically active, vocal. He also won a case against the state of California during the McCarthy era. Very, very active human being, and also scientifically someone whose work I follow. Tolman did behavioral experiments with rats. He would put rats in mazes, let them roam around and learn the environment, and then introduce a reward. And then the revolutionary thing, the cognitive revolutionary thing that he found was that unlike the behaviorist dogma of the time, behaviorism was the dominant point of the time, and it said, oh, you need reward in order to learn anything. And Tolman said, no, my rats learn a model of the world even without rewards. And later, when you introduce a goal or reward, they actually learn the trajectory to that reward faster because of the fact that they have already learned a model of the world. So his idea was that even if we are not rewarded for what we are doing, we can learn models of the world, which I guess explains why a lot of extremely oppressed people still produce knowledge. In the 70s and the 2000s, the Nobel Prize winning place cells and grid cells were discovered in the neurons in the brains of the hippocampus of rodents, where they put the rats in the maze, but they also measured the neurons in their brains as they were firing in some locations, because it's very difficult to do that. They figured out that some cells were firing where the animal is, and some cells are tiling the space of where the animal might be planning in the trajectory. Importantly, as you can see, these concentric circles of different sizes, some of these cells are only where the animal is, and some of them expand further away. And so the goal of somebody like me is to figure out how can we give a computational account of what is the algorithm inside the brain that leads to such a representation of the present and the future in different parts of the brain, in the hippocampus and prefrontal cortex specifically. These cognitive maps, the predictive cognitive maps that have different scales of representation, some of them are just where you are, some of them represent where you want to go, are very common in everyday things, whether it's spatial navigation or hierarchical activities like cooking, making a social inference about who is related to who, or playing chess. Either one of them, you're using these predictive cognitive maps. So a lot of activities that are considered by many people as non-cognitive, for instance, even gossip by the aunties around the block about who is talking to who in the neighborhood in Brooklyn, actually involves a lot of predictive cognitive maps, sometimes as much as chess. So sometimes a person that can't even read or write might be using a very complex model of the world, and their idea of intelligence might be a lot more rich than we think. The way that then I would compare the models is that I would see what kind of matrices of these representations of the world each model would learn. In the interest of time, I'm not going to go too deep into that because I think in 2 minutes I need to wrap up, but I will just show you this. If this is a rodent and it's in this maze, in this panel, in panel B, you can see that this is the representation of just where the rodent is. So this would be a very myopic, I just look at where I am right now. But there is also these predictive representations when you are in a maze. So it's not just about where you are right now, but it's also about where you want to go. And I just want to highlight this notion of the goal policy or reward policy. On the left here, you see what happens if the rodent was roaming around randomly or reward was all over the place. Then the representation that it would show would be sort of lighting up things that are in its brain. The representation would represent things that are close by that it might go. But if the goal was right here at the end of the maze, which was right here, you can see that the representation changes. It's very focused on this one trajectory that is going to go to the goal, which is part of, I guess, the thing about learning and unlearning before you can see what else there is. Because if you're too focused on one direction and you're not unlearning it because you constantly focus on that representation or model of the world, it might be the case that you miss out the fact that there are other paths that exist. One application that this kind of research has is in computational psychiatry. I work on replay and how, for instance, replaying negative surprise events that had negative connotation might lead to maladaptive cognitive maps that represent too much the trajectory to a negative outcome. So just to give an example, this is all artificial agents. There's no human or rodent or biological animal. Let's say the agent starts here and it can go either right or left in the maze. If it goes right, it gets mediocre reward. If it goes left, it gets very good reward if it also goes left again, but it gets a shock if it goes right. So as you can imagine, the optimal behavior is just to go like left, and then get the highest reward after you learn what's going on. But if you replay the shock too much, what happens to the agent is that it avoids going left, although the most amount of reward is there. It keeps going to the other trajectory because although it has mediocre reward, it does not have the shock. And also, if you increase this negative replay, then you reach a point where the animal or the agent or human freezes. In this way, we have a paper where we show how this model can simulate anxiety and avoidance behavior, freezing, depression, where the humans just can't go anywhere, which we published in the Journal of Computational Psychiatry. I don't know how much time I have, but
another 3 minutes.
Oh, perfect.
You need, yeah.
Perfect. So the way to compare human and artificial intelligence in these cases is that we would design specific tasks like the maze I showed you. We would have an experiment where humans come and run the same task. And I will build a model and have the model do the same task. And then I will choose the model. The model that wins is the one that shows a similar behavior to humans. But that's not enough because a number of models might show similar behavior. Then we can compare the neural representations learned by the model with the neural representations that we measure either with fMRI or with electrophysiology in the human or biological agent that we are testing. But another thing that I wanted to, and I mentioned earlier, is that the graph structures of our conversational networks can shape our collective memories. And the wonderful thing is that we can, in a very controlled experiment, we can sort of predict who talks, or we can assign who talks to who first and with which structure. For these kinds of experiments, I have people come and study something alone, 10 people, for instance, and then each of them has a memory test alone. So I know how well they remember what they studied. But then I have them have, let's say every person has 3 conversations, and then they take the test again. Then I can compare their memory before the conversations and after and see how their memories get closer to each other. For instance, if the network of conversations is clustered like this, where the sort of shortest path between, let's say 2 and 10 is very long, or when with just a small adjustment to the structure of the network without changing the number of people or the number of conversations, you make the world a little more compact so people can talk to each other more. And what you see is that we can predict based on graph theory whose memories are going to get closer to each other or further based on their degree of separation, or how many steps there is a distance between them, the shortest path between them. It turns out that, as expected, networks that are not clustered, that are better connected to each other, have a higher convergence in their memories in the second test after the conversations to each other than the one that are clustered and are a little bit more divided. So talking across clusters, it's good because we could potentially integrate our knowledge at some point in a way that is more convergent. So with that, I just want to say that there is a lot to talk about the science, but there is also a lot to talk about the way that the science is done and the places where the inspirations for such science comes from. If you close your eyes in front of one of Ivana's artworks like this one and look at it, as we did for, I think, a whole year in 2010 or 11 in her studio before she designed this, you will see a lot of things come up. A lot of latent representations in the brain that you might not have had access to because you were very focused on a goal or on a reward. But in her case, and there I cite a lot of scientific experiments that were done on similar flashing light stimuli, it's possible to have this experience through this artwork of having representations come to surface and come to consciousness that are not related to any reward, because at this moment there is no goal, there is no reward. You're just sitting somewhere with your eyes closed and there is nothing in front of you other than flashing light. And I think that there is something very liberating and very creative and very exciting about stepping into that dark side of your representations that have been muffled or silenced because of the goals, specific rewards that the world has offered. And I think that, I hope that these kinds of interdisciplinary work is a motivation for all of us to look outside the trajectory that we have gotten rewarded for so long. Thank you.
Thank you, Ida. It was absolutely, again, mesmerizing and in a different way, because I think we're really trying here to unfold a matrix of knowledges, but also, of course, especially knowledge production and knowledge disruption. And I think doing it across the disciplines is absolutely fundamental. You're talking about interdisciplinarity, but at Savi, we often talk about the need to stay in an extra-disciplinary place. So what you're doing is absolutely, with Ivana, interdisciplinary, but then the moment we are trying together to create this new horizon of shared research, is, I think, goes into the even extra-disciplinary place. And your involvement with activism, as you said, in the streets and in the science is something that was very important for us to hear, because often seems that in science, this critical perspective is not so at the fore, not so fundamental, but I'm happy to hear that many other forces, even there, that are trying to undo this systemic racism and injustice.
Exactly.
Thank you.
So to